Good morning, folks. We just handed out our test that we took yesterday that you guys are getting to take today or Thursday. Yay, you. Today we're going to be talking about the nature of electromagnetic waves. It's a short read, 6 homework questions, which of course you'll get in the morning. Well, I guess this morning because you're watching this now. This is confusing. How do y'all keep up with this? Okay. All right, here we go. All right. Have you ever been caught in a rain shower? Of course you have. Okay. You run for cover until it passes so you don't get wet. And believe it or not, you're being showered all the time though. Not by rain, but by waves. Okay. You cannot see, feel, or hear most of these waves. But as you read this, you're going to be right now you are being surrounded by radio waves, infrared rays, visible light, ultraviolet rays, maybe even tiny amounts of X-ray and gamma rays. All these are electromagnetic waves. Okay, gamma rays. That's why I have such a hulking personality. Anybody get that?
No, of course
Gamma rays is what causes Bruce Banner to turn into the Hulk. Okay. Yeah, you got to know your audience. Okay. So anyway, all right. I thought we had a bunch of Marvel fans up here. You knew.
I knew.
Leo knew one thing, so now I've insulted him.
I don't spend in my free time to watch all of the
I would turn the camera and point it at Leo, but I don't want everybody to see him melt down because I insulted him because he said the answer and I didn't acknowledge it. I apologize, Leo.
I don't care about that.
You don't care about that? Okay. All right. You sure did seem like you did.
Why are you leaving?
All right. What is an electromagnetic wave? Okay. If you've seen waves travel in water, rope, and springs, you have heard sound waves that travel through air and water. All of these waves have two things in common. They transfer energy, and they also require a medium to travel through, right? But electromagnetic waves can transfer energies without a medium, which means they can go through vacuum. They don't have to have anything to bounce off of. Okay? So an electromagnetic wave is a transverse wave. Now, everybody remember what transverse waves are? Everybody's hand went up, just so you know. Okay. Longitudinal waves, what we talked about in the last section, and that's the one where it's like a spring. Okay? They kind of come together, and they spring out, and they're moving the particles right next to them. You know, this energy stays here, but it hits this and moves it, right? A transverse wave, but it's going in one direction. A transverse wave is the same thing. It's going in one direction, but it's either doing this or it's doing this. So it's not compressing and springing out, compressing and springing out. It's doing this number.
Yeah.
And because of that, it doesn't have to have a medium to bounce off of. Okay? It can travel in a vacuum. It can travel in empty space. It does not have to have anything. In fact, a medium will actually cause it to slow down a little bit. Take light, for example. Yeah, Caleb?
Doesn't a longitudinal wave need that because it has to compress, but to compress it has to have
It's got to have something, yeah, it's got to have something, energy to feed off of.
You can't, like, when you have a spring, you have to push on it for it to compress, and then it springs back.
Exactly. That's why it has to have a medium. Yeah.
Yeah, but it doesn't need to compress.
Exactly.
The transverse wave.
There you go. That's it. You're exactly right. You nailed it. That's exactly right. Okay? So, an electromagnetic wave is a transferred wave that transfers electrical and magnetic energy. So an electromagnetic wave consists of vibrating electrical and magnetic fields that moves through space at the speed of light. Okay? Can anybody name an electromagnetic magnet that is used to pick up really heavy objects? Anybody think of one?
Hammer.
Well, metal detector, but it doesn't actually lift it, but it does find it.
Junkyard.
Junkyard. The places that crushes cars. The big magnet that picks it up and puts it into a crusher, that's an electromagnetic magnet, okay, is a real strong magnet, but it won't pick that car up until you throw the electricity to it. And then it'll pick the car up, take it over. Because if it was just a strong magnet, it would pick the car up, you would move it over, but then you couldn't get it loose. So the guy has to throw a switch that causes electricity to come through it, it'll pick it up, but then when he kills the switch, it drops it. Yes?
I think, I remember they're building like this new train, but it kind of like hovers over these rails and it uses like magnets.
Yeah.
I can't remember what it's called.
That's impossible.
Yeah, that's it's the levitation thing that we talked.
Yeah, I understand it's like a small version where they have like a spring and they add a magnet and like they put it in, in the tube and it went around and around.
Yeah, I don't know if I want to ride on that. I want something touching the ground somewhere along the line. All right, so light and other electromagnetic waves are produced by charged particles. Every charged particle has an electrical field surrounding it. Okay? So an electrical field produces electrical forces that can push or pull on other charged particles. When a charged particle moves, it produces a magnetic field. And a magnetic field exerts magnetic force that can add on certain materials. Think about a magnet. Okay? If you take magnets and you take the negative side and the positive side and you get them close enough, what do? They come together. But if you take that negative side and a negative side, what do?
You can't get
They repel each other. Yeah, you got to have a positive and a negative to attract. That's where the old expression said, even in relationship, opposites attract. You got to have a negative, you got to have a positive that will pull it together. Two negatives will push against each other. Two positives will push against each other.
I always like playing with the two negatives, like how I made like a ball and I'd always like somehow smush them together.
Yeah, they are
My
fun to
brothers
play with.
and I would used to go and try to push them together, and we succeeded a couple of times. But we just go.
Oh, you can do it, but you can definitely feel the force pushing on you. And we'll do that Monday when we're doing some experiments. We'll actually do that. Okay? And it talks about if you take a paper clip and put it near a magnet, what happens? Do you have to put the magnet right on top of the paper clip?
No.
No. If you get it close enough, that electrical force, the magnetic pull, will cause that paper clip to run across the table to that magnet. Yes?
And the stronger the magnet, the farther away it
Absolutely.
takes
The stronger the magnet, yeah, the more pull it has. Absolutely. Okay? When a charged particle moves, it produces a magnetic field. Magnetic field exerts magnetic force that can add on certain materials. If you place the paperclip near a magnet, for example, the paperclip moves towards the magnet because of the magnetic field surrounding the magnet. When charged particles changes in motion, its magnetic field changes. The change in magnetic field causes electrical fields to change. When one field vibrates, so does the other. In this way, the two fields constantly cause each other to change. The results of an electromagnetic wave, as shown up here in the picture, causes that change. I'm sorry I really wish we still did an introductory to chemistry, because it was fun talking about atoms and all. Because if you know anything about atoms, of course, they've got a certain amount of neutrons, a certain amount of electrons, okay? But when they bond, in order to make stuff, and they become a molecule, when atoms becomes a molecule, they actually share electrons. And there's two different ways that they do that. They can either kind of unite and they'll share a couple of electrons, or one of them will actually give up electrons to another atom.
But that means that
Okay.
an atom would be this.
Well, it's changed, but they're making a molecule. That's what they're doing. That's the whole idea.
But what is the electron?
You have to wait till you take chemistry, dude. You have to wait till you take chemistry now to learn all that. I think your mom does it next year. But yeah, you got two different types of bonding for atoms. Okay. Yes, Brady.
So like when you have two magnets magnets and you put the opposite sides together, why does it like pull apart?
Because the forces are the way that it's set up. Let's just, for example, a positive force might pull, a negative force might push.
Oh.
So if you're pushing, two things are pushing against each other, they're going to repel each other.
Yeah, I get it.
Yeah, kind of like that. I think that's the easiest way to explain it. All right, the energy that is transferred through space by electromagnetic waves are called electromagnetic radiation. Electromagnetic waves do not require a medium, so they can transfer energy through a vacuum or empty space. This is why you can see the sun and the star, okay, because they are traveling through the light from those things are traveling through the vacuum of space, okay? And all electromagnetic waves travel at the same speed in a vacuum, about 300,000 kilometers per second. Now this speed is called the speed of light. And this speed of light from the sun takes about 8 minutes to reach us. How far away is the sun? In miles. About 93,000 miles. Or it's not 93 million miles.
That's what I say.
Not thousand. 93, that would be high. About 93 million miles. And it reaches us in 8 minutes.
That's scary.
That's booking. That's booking. Okay? Yeah, Caleb?
So when it's in space, it's a transverse wave, but then when it comes into like our atmosphere and it bounces off everything, what
It
does
slows
do?
it down. That's
Okay.
kind of like light. Light is going 300,000 kilometers in a vacuum. That's when it's moving its fastest. Once it starts hitting air particles, dust particles, all this other, it slows it down. Still goes a whole lot faster than the speed of sound,
Yeah,
but it's not going 300,000 kilometers
but
anymore.
it doesn't come like a longitudinal wave because it's
No,
bouncing
it does
off
not become.
stuff?
It does not become a longitudinal wave.
Okay.
No, because it does not
It
have
just
to. The
slows it
medium
down.
slows it down. It doesn't have to have the medium to continue to move.
Okay.
Yeah. Yes.
If you do you think if somebody traveled, how long would it take by car to travel that much? Their entire lifetime?
More than that. More than that. Yeah. But scientist says that if you could go to the sun and you had a microscope, a telescope strong enough to look back on the Earth, you would be seeing what happened 8 minutes ago. But you think about it, we talk about in astronomy. If we're looking at a star that is, we can see the twinkle of it, and it is 400 million miles away, and we see the faint twinkle of it, and it takes it, I don't know, let's just say it takes 2 years for the light to reach us. That star could burn out, and we would still see its light for 2 years. Because the light is already traveling through time.
That's pretty scary.
Because the light that we're seeing left it 2 years ago.
Talked about that with Beetlejuice.
Is that not cool?
Yeah.
That's kind of mind-blowing if you think
Wait,
about
so
it.
when you
That's
said
pretty
that the
mind-blowing.
sun, if we took a strong enough magnifying glass, we could see what happened in 8 minutes. Doesn't that go against what Albert Einstein said about we can always go?
It
to
was.
the future?
It was. In fact, we'll talk about that in a minute.
Wait, imagine taking a ginormous mirror and then focusing all the sun's rays and then putting a smiley face on the moon.
Mr. Seidel.
Yes.
That would be
All right, stop. Yes.
Could we maybe take a trip to the moon?
Absolutely. Absolutely. In fact, I saw where a Japanese billionaire is offering to pay your way to the moon if you want to go. Yeah, he's selecting 8 people. All right, let me do a little bit more here. Okay.
There you go, bro.
Most properties of electromagnetic waves can be explained by a wave model. However, some properties are best explained by a particle model or particle models. As you have learned, light is an electromagnetic wave. Both wave models and a particle model would need to be used to explain light, the properties of light. Okay? The lens of many sunglasses, like the one shown down here, polarized filters. Okay, most of you have those, the sunglasses, polarized sunglasses. The light acts as a wave when it passes through a polarized filter. Ordinary light has waves that vibrates in all directions, up and down, left and right, okay, and other angles. A polarized filter acts as though it has a tiny slit, okay, that runs this way. That is why if you take them You got two lenses and they got tiny slits that allows light in this way, and you take one of them and turn it this way. Now the slit, one slit is going here, and on the other one it's going this way. It blocks the light. Light can't pass through it. That's fine. You can photo it. We'll do that experiment on Monday. Yes.
Maybe we'll get Miss Frizzle in the back of the school bus.
Maybe. All right.
Yeah, maybe then we can go to the moon.
Only some light waves pass through a polarized filter, and the light. So some light has got to pass through. Otherwise, you wouldn't be able to see. You'd put them on. Your parents would be going down the road, driving, and the sun be in their eyes, and they say, "Hey, hand me my sunglasses." And they put their sunglasses on, and now all of a sudden they're all over the road because they can't see. So some light does pass through. Okay, don't misunderstand. Okay? But it's not. It does block most of it. Okay. The light that passes through vibrates in only one direction, though, and it's called polarized light. No light passes through two polarizing filters that are placed at a right angle of each other. To help you to understand the wave model of light, think of waves of light being a transfer weight of a rope. And it talks about if you put a rope through a picket fence and you're going up and down with it, it goes through the opening without any problem, right? But if you start taking it going this way, it stops because it's going to start hitting the pickets, right? So it's got to go one way in order to make it, okay? And that's what it's talking about. Sometimes light behaves like a stream of particles. When a beam of light shines on some substances, it causes tiny particles called electrons to move. And the movement of electrons can cause an electric current to flow. Sometimes light can cause an electron to move so much that it is knocked out of a substance. This is called the photoelectric effect. The photoelectric effect can be explained only by thinking of light as a stream of tiny packets or particles of energy. Each packet of light energy is called a, what? Anybody know what it's called?
Photon.
Photon. Not, yeah, it's a photon, not proton, but a photon. Okay? Albert Einstein first explained the science behind the photoelectrical effect in 1905. Okay? So, pretty. Now, Einstein, that was the beginning of his string theory. Okay? Again, it had been proved, that's why it's string theory, not string fact. But he was standing, I think I've told y'all this before, he was standing out under a street light. And it started misting rain. And he looks up and he sees the way the rain particles are acting as they come past the light. Where I would be going, ooh, I need to get in and out of the rain, or wow, pretty. He went, oh, that must be how light travels. And he goes in and does a whole equation and attempts to prove how all the universe works. There's a difference in Einstein and Sizemore right there. Okay? All right. Bye.